Okay, so welcome everyone to another TCS Plus talk. We're really happy to have Christian Coester here from the University of Oxford, and he'll tell us about the randomized case server conjecture and how it's false. So before we get started, just a few comments. So I am recording the talk, but I do want to encourage everyone to keep their cameras on and give Christian some visual feedback, as well as ask any questions. But there will be an unrecorded, maybe hangout session after the talk. And then finally, before we get started, let me thank the rest of the organizers. TCS Plus is really a big effort. It takes a lot of us. So with that said, big thanks to Clement Canon, Rachel Cummings, Anindya Day, Sumega Garg, Gadam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens-Davidowitz, Tomas Vedik, and David Weiss. And with that said, then, all right, let's get started. And Christian, please take it away.
Okay, thank you very much for the introduction, Eric. And yeah, thank you for inviting me and for organizing this. So yeah, this is joint work with Sébastien Bubeck and Yuval Rabani. And it's about the K-server conjecture, or the randomized K-server conjecture. So let me start by introducing the problem, the K-server problem. So in this problem, we are given a metric space, and there are K-servers located in this metric space. And now at every time step, one point in the metric space is requested, and we have to serve this request by moving one of our K-servers towards the request. So let's say there's a request here. Now we have to decide which of our, in this example, 3 servers do we move towards the request. And then another point is requested, and again, we have to decide which of our K servers do we move to the request. And the goal of the algorithm is to select the servers such that the distance traveled by all the servers together is as small as possible. Now, the problem here is that this is an online problem. So that means that the algorithm has to decide which server to send to the request before knowing about the future requests. So the locations of the next requests are not known. And as is usual in the area of online algorithms, to measure the quality of the algorithm, we look at the competitive ratio. So we say that an algorithm is row competitive if the cost of the algorithm is at most row times the optimal offline cost plus maybe some constant. And this constant here, this is anything that can depend on maybe the initial configuration and the metric space, but not on the request sequence. And what I mean by opt is really the best cost that could be achieved by some offline algorithm that knows the entire sequence in advance. And of course, because we have incomplete information, we cannot achieve a competitive ratio of 1 here, but we want to get this as close to 1 as possible. And yeah, so the K-server problem is also often called the holy grail problem of this area of competitive analysis. So let's first discuss what is known about this problem and what the conjectures are. So first of all, there is the K-server conjecture. So this is the statement that there exists a K-competitive algorithm that is deterministic, and this is still open, although we know quite a lot about it already. So on the one hand, there's a lower bound of K on every metric space of at least K plus 1 points. Like if we have K points only in the metric space, then of course the problem is trivial. You just put a server at every point and you don't have to move at all. But on every metric space of at least K plus 1 points, there's a lower bound of K for every deterministic algorithm. And moreover, there's an upper bound of 2K minus 1. So this K-server conjecture is resolved up to a factor of 2. And there are many special cases where, in fact, we know that there exists a K-competitive deterministic algorithm. So many special cases where we know that this conjecture is true. And then there's the randomized K-server conjecture, and this is the setting that we're going to talk about today. So this conjecture states that there's a log K competitive randomized algorithm. So if the algorithm is allowed to use randomization, then for many problems, it's known that this can improve the competitive ratio, and also for special cases of K-server, this is known. So what's the state of the art? Well, on the one hand, there's a lower bound of log K over log K, which is true for every metric space of at least K plus 1 points. And in terms of upper bounds, there are upper bounds which are polylogarithmic in K and some other parameter. So for instance, there's a log square K log N competitive algorithm for every metric space of n points. And there's also a log cube k log delta competitive algorithm where delta is the aspect ratio, so the ratio between the biggest and the smallest distance in the metric space. And yeah, but both of these upper bounds are relatively recent. Like we've only had a polylogarithmic algorithm since like, I think about 10 years ago or something. So this took a lot of time to get actually any polylogarithmically competitive algorithm. And here also for many special cases, it is known that the competitive ratio is exactly log k. So for many special cases, this randomized Coester conjecture is known to be true, but it has remained open for the general case. And yeah, so here's just the statement again of the randomized Coester conjecture. And in our paper, we prove this statement, well, almost this statement. I need to make a small change. So this is the theorem that we prove. K-server conjecture is not true. There's no such algorithm. And to be more precise, what we show is that there exists some metric space of k plus 1 points where the competitive ratio is at least log square k. And we also show another result, which is a universal lower bound. So I mentioned on the previous slide that there's this log k over log k lower bound. That's true for every metric space. And we improve this to log k for every metric space of at least k plus 1 points. So this universal lower bound is therefore tight because there are metric spaces where we know a matching upper bound. Okay. And yeah, so the focus of the talk today will be this first of these two theorems, or the middle one on the slide here. But to prove it, I want to first define another problem, which is called metrical task systems, and which anyone that has done research in online algorithms has heard of, I'm sure. This is one of the most general problems in online algorithms. It's also a generalization of the K-server problem. So how is this one defined? We are also, again, given a metric space. And now it's a finite metric space of n points. And instead of having k servers, there's now only one server in this metric space. And let's say that this server is initially at some location p0, just some point in the metric space. And now at every time step, we get a cost function. So this cost function is a function that maps every point of the metric space to some non-negative number, possibly infinite. And after this cost function is revealed, the algorithm then chooses a new point, pt. So this is the new location of the server. And then the algorithm has to pay movement costs, so the distance from the old to the new location. And it also has to pay service cost, which is the cost function evaluated at the location that the algorithm moved to. And yeah, so this problem actually, if the cost function only takes values 0 and infinite, then it is equivalent to the n-1 server problem. So to the special case of the K-server problem in that same metric space, where the number of servers is one less than the number of points in the metric space. So to see that this is true, yeah, notice that if there are n-1 servers, or in other words, if we have a metric space of k plus 1 points, then there's always exactly one point in the metric space that's not covered by a server. So let's call this the anti-server location, the location where we don't have a server. Now the anti-server in the K-server problem on a k plus 1 point space corresponds to the one location of the server in metrical task systems, in the sense that if there's a request to some point in the K-server problem, then we can represent this by the cost function, which assigns cost infinite to this point and cost 0 to every other point. So this is forcing the anti-server to move to some point that's not requested. And equivalently, this means that therefore the requested point will not have an anti-server, so it will have a server. And this is essentially the argument why these two problems are equivalent if we have a metric space of k plus 1 points. And to prove the lower bound, we will then actually consider, well, we will use this language of metrical task systems rather than K-server, because that will be a bit simpler to think about. So what our lower bounds imply are therefore also new lower bounds for metrical task systems. So on the one hand, it shows that there's an existential lower bound of log square n. And by existential, I mean there exists a metric space where this lower bound holds. And this is tight because we know for every metric space of n points that there's also a log square n upper bound. And moreover, the universal lower bound gives us a log n lower bound for all metric spaces of metrical task systems. And this again is tight because we know that on some metric spaces, there is a log n upper bound. So in that sense, it completely settles the randomized competitive ratio of metrical task systems. Okay. By the way, I'm happy to take questions in between. So if there are any questions already, then this would be a good point to interrupt me. But also, if there's some other time, feel free to just interrupt me or post in chat or anything. Okay, so let's continue then. So before I show our new lower bound, let's actually consider the previous lower bound, the previous best existential lower bound of log n. So this was shown in 1987, back when the problem was first introduced, and it's quite a simple argument. So let me show it to you. So the metric space is the uniform metric. So that means that the distance between any 2 points is 1, except that the distance from every point to itself is 0, of course. So we can think of the metric space as a star. And the cost function that we receive at time t is the following. So there's some point rt, which is chosen uniformly at random from the points of the metric space. And now the cost function assigns cost infinite to this point and cost 0 to all the other points. Okay, so there's this point, for instance, which gets cost infinite, and all the others get cost 0. And then the next cost function comes, and so on. So this means that every algorithm, whenever it is at the location that gets the infinite cost, then the algorithm has to move to some other point. So what is the cost of the online algorithm? Well, in every step, the probability that the algorithm gets hit by the cost function is 1 over n. And if that happens, then it has to move to some other point. So it has to pay cost 1 with probability 1 over n for each request. So therefore, the expected cost of any online algorithm is the number of requests divided by n. And what about the optimal offline algorithm? Well, that algorithm can look into the future, so it can choose in a smart way to what point to move next. And the best way to do this is to move to the point whose next request is furthest in the future. So now this essentially is kind of a coupon collector question, like how many cereal boxes do you need to collect until you have each of n coupons, or in this case, how many requests does it take until every point is requested once since the time when you last moved? Well, it takes n log n requests, roughly. Like this is the classical coupon collector argument. So therefore, the expected offline cost is the number of requests divided by n log n. And then the lower bound of log n follows by just taking the ratio of these two quantities. So this is a standard application of Yao's minimax theorem. So instead of describing a deterministic request sequence, we describe a randomized sequence and then look at the expected cost of the online and offline algorithm on this random sequence. And the ratio that we get there corresponds precisely, that gives us a lower bound on the competitive ratio of the best online algorithm. And also, the minimax theorem of Yao is more general in the sense that every you can actually achieve the best lower bound always with an argument of this type, where you construct the request sequence randomly, and you can then in fact pretend that the online algorithm is deterministic. And we will also use this minimax theorem in our proof. Okay, so how can we improve over this simple argument and improve the log n to a log square n? So here's some intuition. So it turns out that the proof idea is actually contained in a poem that's more than 100 years old. So let's just discuss this. So two roads diverged in a yellow wood. Now our online algorithm has the problem that it cannot travel both of them. So it will just start traveling down one, but then maybe switch to the other because, well, yeah, it then turns out they're about the same. So it keeps going on the other one and like waits for another day to switch back, but then doubts may creep up. Maybe the other one would have been better. And then in the end, we have a change of perspective. So the offline algorithm is the one that will take the road less traveled by, and that is what will make all the difference. Okay, and we just apply this poem now recursively, and then you might see already that this gives a log square n. Okay, so I realize I still have some time left in my talk, so in case someone is not convinced yet, I'm willing to make this a bit more mathematical. So let me actually prove a slightly weaker bound first. Let's consider, yeah, well, the goal of the next slides is to prove a lower bound of log n over log n squared. So almost log square n up to some log factor. It's yeah, I'm going to show this because it's a simpler proof. Yeah. Okay. So we will construct a metric space recursively, and I will always, yeah, I will use this symbol for the metric space, MW. So we will, W is some integer parameter that we will increase as the recursion goes up. And there will be two special points in this metric space, the leftmost one and the rightmost one. And the request sequence that we construct, it will be random. And it will, okay, one thing I should have reminded you of, we're taking this metrical task systems perspective here. So there's one server, and we can give costs infinite and 0. And I will, in my pictures, I will use this white bar to indicate that the where the points where the cost function is 0 are only points under the bar. And so everything not below this white bar has infinite cost. So the algorithm has to be somewhere below the bar, but maybe not all the white points under the bar have cost 0, but just some of them. I'm just using this to, yeah, if you zoom out, then it just means the algorithm has to be somewhere in this region. Okay, so the random request sequence will be such that the servers, the one server starts at this leftmost point, and then it will somehow request points in the metric space that slowly force the server to move to the right. And at the end of the request sequence, the server will be at the rightmost point. And moreover, we will do this in such a way that the optimal offline algorithm can serve all the requests by moving along a shortest path from the left to the right. And the distance from the left to the right is also the diameter of this metric space. So the optimal offline cost will be the diameter. The online cost will be at least RW. So this is the lower bound on the competitive ratio that we're going to prove. So the online cost will be at least RW times the diameter. So as base of induction, you can just use a path, and then the cost functions are just yeah, slowly forcing the algorithm to move from the left to the right, but always shifting the one point that has cost 0 to the right in each request compared to the previous request. And now how do we do the inductive step? So this is how we construct our new metric space, MW plus 1. So you can see it has, again, this shape that there's this special leftmost point and this special rightmost point. And we use lots of copies of our recursive metric space, MW. And I can tell you how many copies we use. We use 6 RW copies, where RW is our lower one that we want to prove. So there are 2 paths, essentially, from the start to the end. One path of 3 RW copies at the bottom, and another path of 3 RW copies at the top. And let us think of these 3 RW copies on each branch as partitioned into 3 groups. So we have this first group of RW copies, the second and the third one. Okay, now this is the metric space. Let's now describe the request sequence. So we will, of course, call our reductive, our recursive request sequence in these copies. And we will start by calling the recursive request sequence simultaneously in the first two copies, like the first at the top and the first at the bottom, and then the second at the top, second at the bottom, and so on. So this is forcing the algorithm to move along one of these two branches, some distance forward. And yeah, now after this, the algorithm must be at one of these 2 points. But, well, nothing really happened so far, right? Like we didn't do anything smarter than what we did in the at the previous level of recursion. The only point of this is to ensure that the algorithm is now at one of 2 points that are far apart from each other, and the algorithm doesn't know which of them is the better point. So now in the second stage, okay, actually let's, at the same time as I'm describing the request sequence, let's also do the analysis already. So what's the cost of the algorithm? Well, so far, we have had to traverse through RW copies of the recursive space. And in each of these copies, we had to pay a cost of at least RW times the diameter of this copy. So the total cost so far is at least RW times the diameter. And of course, switching doesn't help here. So you cannot get a lower cost. So now in the next stage, we're going to flip a coin. And depending on whether we get heads or tail, we will advance one of these 2 copies forward. So we flip a coin, and then well, if the algorithm was here with its server, then it had to move forward, paying at least RW times the diameter. If the algorithm wasn't here, but it was here, then it doesn't have to pay anything in this step. And now we flip another coin, and let's say this time maybe the coin tells us to advance at the top, and we keep going like this. And of course, the algorithm could consider jumping to the other side, like switching to the other branch, but because we have so much distance between these 2 points, switching would cost at least 2 RW times the diameter, and that is so expensive that it basically doesn't help the algorithm. So it's better to just stay at the current copy and pay this expected RW times diameter cost. So we can essentially ignore the case that the algorithm switches and pretend that it doesn't switch because it doesn't help. And we keep flipping coins in this way, always advance one of the 2 copies randomly. And we do this for RW steps. So each step hits the algorithm with probability 1/2. So therefore, the expected cost of this second stage is 1/2 times RW, because that's the number of copies, the number of times that it got hit, times RW times the diameter, which is our low one from the reduction, from the recursion. And now, after this stage, notice that typically one of the 2 branches will be more advanced than the other one. And well, how much more advanced? Well, because this is like the gap between them is roughly normally distributed by the central limit theorem. So there's a gap basically of a plus minus square root of RW. And this is what will make all the difference in the proof here. So we are now going to kill the more advanced path. So we are going to give infinite cost at this location, which previously had cost 0. So this is ensuring that any algorithm now must be at this location. And now we will continue calling again recursive request sequence on the remaining copies of this less advanced branch, and thereby forcing the algorithm to move to the end, to the rightmost point. So for this last stage, what is the cost? Well, in each copy, again, we have a cost of RW times the diameter. How many copies are there? Well, there are RW copies here, half RW plus square root RW copies here. So this is the new contribution of this last step. And yeah, we can, this is the entire request sequence. And now we just need to analyze it. So, okay, let me just go back. So yeah, if you add this together, then you get this as the lower bound on the total cost of the online algorithm. The offline algorithm can serve this more efficiently because it knows in advance which of the two branches will get killed. So it will just choose the correct branch and move towards the end and go paying only the diameter in each individual copy. So the offline only pays 3 times RW times the diameter of the individual copies. Okay. And now to get a lower bound, we just need to divide these two quantities. So we want to calculate RW plus 1, so the lower bound on the competitive ratio at the next level of recursion. So let's take the ratio of these two. And to satisfy this, we need to choose RW to be at most, at most this ratio, and that means at most RW plus square root of RW over 3. By the way, I'm hiding, actually there, if I were a bit more precise, there would be another constant factor here, because from the central limit theorem, there's another constant factor here, but let's ignore this for now. And this recurrence is solved, for example, by choosing RW to be W square over 81. So it is basically quadratic in W. Okay, but now we wanted to express the lower bound not as a function of W, but as a function of the number of points in the metric space. So we just need to relate the number of points in the metric space to W. So N is size of the metric space. By construction, well, we used 6 RW copies of the recursive metric space. And then, by induction, just plug in all of these numbers. So we get the product of all this. And now for our I, we can plug in I square over 81. So it's 6 Ri is at most I. And then this is W factorial squared, which is exponential in W log W. And therefore, in other words, RW is, well, we said it's W squared. So as a function of N, it would be log N over log N squared. So that's basically the whole proof of this, of almost our main bound. Like we're just losing this log. Okay. Any questions? Okay, so then let me tell you a bit about how to remove the log. So the idea is basically, I mean, can't we do the same argument, but with a smaller metric space, so that instead of having n equal to 2 to the W log W, if we have something like n equal to 2 to the W, then we would get what we want, right? Then we would get a log square n. So that is essentially our approach. So instead of using 6 RW copies of MW in the recursive construction, we only use 6. And then the size of the metric space will be 6 to the W. Now, the problem with this approach is that in this second stage of the request sequence, we wanted to flip many coins in order to create this square root RW gap. But if we have only 3 copies on each branch, well, then we cannot, like after flipping 3 coins, we would have possibly already, well, I mean, after just a constant number of points, we would have reached the end, and that's not enough. So the problem is that each call of the recursive sequence would advance too much already. And the way we solve this is that rather than calling the recursive request sequence all at once in each step, we only call a little piece of it. So we advance the recursive sequence only by a chunk, and then a next chunk when we again flip the coin that tells us to advance on that side. Okay, so to make this formal, we need a more refined induction hypothesis that gives us lower bounds on each chunk of the request sequence that allows us to break the request sequence into smaller pieces. So the key lemma that we are proving in the paper, I will not prove it here, but I will state it, is that for every W, there exists a random request sequence of chunks. So by chunk, I just mean a smaller request sequence. So there's a sequence of sequences, and each Ri is such a subsequence. And there are random variables Ci, such that the cost of the online algorithm on this chunk rho I, conditioned on what the earlier chunks were, is at least this CI. So CI is also a random variable, but it's some like measurable function of these earlier random sequences. So we have a lower bound on the cost in each chunk, and the sum of these lower bounds in expectation is at least W squared times the optimal cost. So if we have both of this together, then I mean we just sum up the cost over all the chunks, and we would get this W square lower bound, which would then imply overall a lower bound of log n squared, because we said that n is 6 to the w, so w is log n. And the other property we need in this lemma is that the size of each, like the lower bound for each of these chunks, is roughly the optimal cost. By roughly, I mean it's up to some small constant factor, but it's actually a random number. And the reason we need this is that, well, on the one hand, we don't want the CI to be too large, because if the cost of each chunk is too large, then the algorithm would just switch to the other branch, and that would be too cheap. But we also don't want the cost of the chunks to be too small, because then the gap that we create when we randomly advance on one of the two sides would be too small. So it really needs to be just the right size. And to prove this, I just give you these 3 lines of proof ID here. So essentially, we will proceed as before, but now we are not going to flip fair coins, but biased coins. And because what we want to ensure is that the expected cost that we suffer if we use the top path minus the expected cost if we use the bottom path, that is a martingale. And we have to use a biased coin because the CIs are not, like, they are not all the same numbers. They are, in fact, random numbers, and they don't have exactly the same values. But now we can do something similar to what we did before, where we had this square root RW gap by applying the martingale version of the central limit theorem, or the Berezin theorem that tells us how fast this converges to the normal distribution. And that will give us a similar gap of, well, corresponding to the square root of our lower bound. So a gap of roughly like W times the optimal cost. And then we can do calculations as before and get a similar recurrence. Now, the only other thing we have to be careful about is that we wanted to ensure that these lower bounds are always of roughly a certain size. So we will actually at first construct some smaller chunks, but then we can combine them and thereby get the CIs of the right size. Okay, but yeah, I just wanted to give some idea of how this is done without too many details. Okay. So yeah, let me just mention that the metric space we use, as I said, is similar to before, but we use 6 instead of 6 RW copies in each recursive step. And this is actually very similar to a family of metrics that has been known as the diamond graphs. So they are just constructed by taking 4 copies and gluing them together. So these are the first 3 diamond graphs. And yeah, I think it's quite interesting that these metrics play an important role here as well. So yeah, as I mentioned, instead of taking 4 copies, we use 6 that we glue together. So then the metric space looks like this. And if you have very good eyes, then you can see a small circle here on the left of the screen. So we take 6 of those, glue them together, and then 6 of those, glue them together, 6 of those, and so on. So this is the family of bad metric spaces on which this lower bound holds. Okay, so let me make some further remarks. So yeah, we get this log square n lower bound for MTS, and it is actually tight for MTS because there are algorithms that achieve this on every metric space of endpoints. And what these algorithms are based on is to approximate the endpoint metric space randomly with an HST metric, and then run an algorithm on this HST metric. And this embedding step loses a log n factor. So there's a log n competitive algorithm for HSTs. Now you approximate the arbitrary metric with an HST, which loses another log n, and this is how these log n upper bounds are achieved. And yeah, one of my favorite problems was to try to get a better algorithm that avoids this loss of the distortion, because I mean, everyone kind of thought, well, this distortion loss must be avoidable. But yeah, interestingly, it turns out this is not avoidable. This is actually the best thing you can do to approximate the arbitrary metric space by an HST. So yeah, I don't have this problem anymore of trying to improve this algorithm. And what our lower bound also implies is improved lower bounds for a number of other problems. So K-taxi, distributed paging, metric allocation. And also very similar construction allows us to tighten the lower bound for the Lloyd graph traversal problem. So for this problem, we recently showed an upper bound of k square, and that upper bound actually what has been part of our inspiration for improving this lower bound. And yeah, just modifying our construction very slightly, we get a lower bound that is matching this upper bound up to a constant factor. And yeah, as I mentioned before, we also tightened the universal lower bound, so the lower bound that holds on every metric space, which previously was log over log log, and yeah, the parameter is k for k server or n for MTS, and we improved this to a single log, which yeah, as I mentioned, is also tight. And the idea here is essentially the same what I mentioned before with the chunks. So take the existing lower bound proof that gives you this log over log log, and modify it in this chunk by chunk recursion way, and then you get a single log. Okay, and yeah, I realize I'm faster than I thought, but so I'm already on my last slide. So let me conclude. The competitive ratio of metrical task systems is log n on the easiest metric spaces because of our universal lower bound and the existential upper bound that exists. It's log square n on the hardest metric spaces because of our existential lower and existing universal upper bound. For k server, it is log k on the easiest metrics of at least k plus 1 points. Below it's trivial. It's log square k on the hardest metrics with exactly k plus 1 points. Or in fact, you can also say k plus a constant many points. But there's still a very interesting and exciting open question here, which what is the competitive ratio of k server on really the hardest metric spaces of any number of points? So we have this improved lower bound of log square k now, but the upper bounds are still, if they are polylogarithmic, requiring dependence on some other parameter. Or if you don't allow this dependence, then we don't know any better algorithm than the deterministic one, which is 2k minus 1 competitive. So that's really a yeah, very, very exciting open question. And yeah, let me just recall the main takeaways. So diamond graphs are cool, unless you're trying to traverse them quickly. If you're trying to shove off a log-log somewhere, and it's a recursive argument, consider whether you can break the recursion into chunks. And finally, don't forget to look for proofs in old poems. So thank you very much. Yeah, I'm happy to take any questions.